So I have told you that in the elastic regime in LEFM, G and J are the same. They have the same meaning. However, J is a more general quantity which is not restricted to linear elasticity. We have discussed this. Now, in the previous video, we had looked at how to find J using a domain integral representation. So that method we will come back to it when we do elastoplastic fracture mechanics. In this video, I'm going to go back to calculating stress intensity factors, which are hallmarks of the linear elastic fracture mechanics, and we are going to discuss a method called the method of interaction integrals, which is very closely related to the weight function method that I discussed at the beginning of this week. So what I'm going to talk is based on these two papers, especially this paper, from where most of the things are taken, and also obviously the book by Kuna. So the idea of interaction integral is the following. It is based on the principle of superposition. So we consider two load cases. So load case 1, in load case 1, it is the actual loading of a cracked body. This is the load case where we actually want to find the stress intensity factors, and we take an auxiliary load case. So this is also called an auxiliary load case, where we have a case with a known stress intensity factor, and we use the connection between these two to find the stress intensity factor in this case. So consider a situation where we superpose the two load cases. So load case 1 and load case 2. Then the displacement superpose. This is a linear elasticity problem. So the displacement superpose, the stresses superpose, the strain superpose, and as we know, the stress intensity factors also superpose mode wise. So mode 1 stress intensity factor superpose, mode 2 stress intensity factor superpose, but not across modes. We have learned that. So we will use that fact as well, but for the time being, let us assume that Ui is the displacement field in the superposed problem, consists of U1 and U2. Similarly, sigma ij and epsilon ij are the stress and strain fields in the superposed problem. Now, the energy momentum tensor was given by this, right? And for the linear elastic case, W is of the form half sigma ij epsilon ij, which is half C I j k l epsilon k l epsilon ij, which is also can be written as half of epsilon pq C pq mn epsilon mn. I have used, instead of ij, I have used pq and mn, and this is your energy momentum tensor. Now you have, this is for the general case where you have a superposed displacement fields and stress fields. So into this we will now add the individual stresses and strains. So we can do this. So we have bkj is equal to half so this is what we have, and now we replace this with epsilon pq1 plus epsilon pq2. We replace this with epsilon mn1 plus epsilon mn2. We replace this with sigma ij1 plus sigma ij2, and this by ui1 comma k plus ui2 comma k. So these replacements we do for both the problems. This is the same. So when you do this, this is what you will end up with. You have epsilon pq so let's this first term, and when you split this up, you will get half epsilon pq1 c mn pq epsilon mn1. So that takes care of this times this times this. Then you will have half epsilon pq2 c mn pq epsilon mn2. So this times this times this, and then you will have two more terms which will be cross terms. So you will have epsilon pq1 half of c mn pq times epsilon mn2, and then you will have half epsilon pq2 c mn pq times epsilon mn1. So this similarly, when you do it for the second term, you will get a similar set of terms. So the second term can be written as sigma ij1 plus sigma ij2 times ui comma k1 plus ui comma k2, which gives you sigma j1 ui1 plus sigma j2 ui comma k2, and then the cross terms sigma j1 ui comma k2 plus sigma j2 ui comma k1. So these are cross terms. So these two terms and these two terms together will constitute what we call BKJ1, 2. These are the interaction terms. This and this will together form BKJ1, and this and this together will form BKJ2. So BKJ in this case will constitute of BKJ1, BKJ2 and BKJ1 comma 2 according to this superposition principle. Now note that, let me erase this. In the interaction term, this one, these two terms are actually the same, because epsilon pq1 times c mn pq epsilon mn2 is same as, based on the symmetry of this, c pq mn epsilon mn2, which gives you sigma pq2. So this is this becomes epsilon pq1 sigma pq2, and here also you will see that you can convert this into the same thing. So uh, this times this is sigma pq2, and this is epsilon mn1. Sorry, this is sigma mn2, this is epsilon mn1. So this term and this term are the same, both have half in it. So altogether these two terms will give you epsilon pq1 c mn pq epsilon mn2. So this is the result of these two terms, and then you have in bkj12 you have contributions from this as well, which I have just erased. So if you put all this together, this will be your bjk1, this will be jk2, and this will be jk12, out of which we have shown that this term and this term are actually the same. So bkj12 will become this. This is what I derived just now. Now when bjk12 is this, remember that the jk integral is a cyclic integral over bkj nj ds. This is what it is, what jk is, and this is consisting of 1 plus bkj2 plus bkj12. Since it has three parts, we will also split this into three parts. So for corresponding to bkj1nj, we will have jk1. Then corresponding to bkj2nj, we will have jk2. And then corresponding to bkj12, we will have jk12. So we will also split the jk into these three parts. We can do this. Now we are basically interested in J1 because J1 is related to the J integral, right? So for J1, we so this is JK12. This is what it will come to. This is your BKJ12. We have proved this. BKJ12 and NJ. And we will now put k equal to 1 because we want jk, and then if we evaluate it over a contour which is not cyclic but starts on the lower crack face and ends at the upper crack face, we will end up with j12, and for j12 we have to put k equal to 1. So that's what I have done. This is j1 and this is ui comma 1, this is also ui comma 1. So this is the interaction integral that needs to be calculated, and to calculate it, we can use the domain integral method that we use. This is a contour integral over a contour gamma. So this integral can be calculated just like the contour integral for J1 that we showed with the domain integral representation in the previous video. So this will be actually calculated with the domain integral. The expression is different from the expression for J1 that we used in the previous video, but the procedure is exactly the same. So you will multiply this by a function q, take the contours and apply the divergence theorem to convert this into a area integral, and that area integral is easily evaluated. In fact, it's evaluated in exactly the same way as the area integral in the previous slide. Now we are dealing with the elastic case because this is these expressions are valid for the elastic case only, and in the elastic case we can also superpose the k's. So mode wise, the k1 for the superposed problem will be k1 1 for the load case 1 and k1 2 for load case 2. Similarly, k2 will be k2 1 plus k2 2. This is for the auxiliary case, this is for our load case, and then the total, we know that G is 1 by E prime in the K1 square plus K2 square. In place of K1 we put K1 1 square plus k1 2 square plus 2 k1 1 k1 2, and for k2 we do the same, and if we do it, this is what you will get, and out of this term is called G12, the interaction part of the of G. This is G2 and this is G1. So we have split up G into three parts, and this interaction part, this whole thing together should be equal to J, and in particular this interaction part should be equal to J12. There should be a 2 here. So G12 should be equal to J12 in the elastic case, and therefore if I can calculate this J12, I have a relation between J12 and the stress intensity factors in load case 1 and load case 2. Load case 1 is what we want to find. Load case 2 is an auxiliary case for which we know the solution. Now we can do it in various ways. We can use these cleverly. The second case, we can choose it cleverly, and what we generally do is the following. Before that, if you know, so you need to know two solutions to solve this. You need to know two solutions. And these two solutions, let us call two auxiliary cases, 2A and 2B. So these are my auxiliary cases for which I know the solution. So for auxiliary case 2A, this is what you will get. You will get an interaction integral J1 2A, and for auxiliary case 2B, this is the interaction integral that you will get. These interaction integrals are basically the solution of this integral in the combined case, and these two interaction integrals are known, and they are in terms of k1 2a, which I know, k2 2a, which I know, k1 2b, which I know, k2 2b, which I know. These are known auxiliary cases. K1 1 is what I want to find, k2 1 is what I want to find. So now if you use these two expressions, these are linear expressions in, and these things you have evaluated from your finite element results using this domain integral, this contour integral converted to a domain integral. Okay, so now the left hand side is known. In the right hand side, these things are known, and this is a simultaneous set of simultaneous equations in this quantity and this quantity. We can solve it. This will be the result of that, and from here we can do it in a we can find k1 1 and k2 1 in a general case where this and this and this are known. But we can do something a little cleverer. We can choose two cases. This first case can be one where k2 2a is equal to 0 and k1 2b is equal to 0. So these are the two cases that we choose. So in the first case, this is equal to 0. So k1 1 will simply be e prime j1 2a by 2 k1 2a. So that's from here, and k2 1 will be equal to j1 2b e prime divided by so from this I can get k2, and from this I can get k1. So first I find the mode 1 part, and then I find the mode 2 part. So that is what is generally done. These two expressions are used, and in computations, as I said, the interaction integral is generally calculated using the domain integral method. And what do we use for the 2a and 2b cases? We can, for example, use the Williams solution with a stress intensity factor of 1. So first we can use as K1 2a, we can use the mode 1 Williams solution with K1 equal to 1, and for K2a we can use the mode 1 Williams solution with K2 equal to 1, K1 equal to 0. Here K2 is equal to 0. So if you do that, you will immediately get the stress intensity factor for any problem. Using the interaction integral, provided you can evaluate, you have a routine to evaluate this interaction integral using the domain integral technique that we learned in the previous video. So that completes my lectures on numerical methods in fracture mechanics. We will not do any more numerical methods in this course. So if you are interested in knowing more about numerical methods and how they are implemented, I have mentioned this before. This is the book to go to. This is the book to go to. This is a good book which has a lot of information on how to use fracture mechanics in finite elements. The individual papers for the different methods I've mentioned, so you can go back to them as well. Okay, so let's stop here.